Okay, welcome again in my online session on medicinal chemistry. In this session, we'll talk about antibacterial sulfonamides. Now, let us see how this sulfonamide class of drugs were developed. The Gerald Domark, he was working on a red dye, that is a prontosil. This is a red dye, prontosil, a structure of red dye. And he was trying to test it for its antimicrobial action. While experimentation, he observed that this prontosil don't show any antimicrobial activity in vitro. Means it doesn't show antimicrobial activity on a Petri plate outside the body. But surprisingly, he observed that if this prontosil is administered to the living system, then it shows antimicrobial effect or antibacterial effect. Then he tried to find what is the reason that prontosil, it is not showing activity outside the body, but it is showing antibacterial activity inside the body after administration. Then he found that this prontosil in body breakdowns this azo linkage. This is called as azo linkage, where it breakdowns and form a compound, that is sulfanilamide. This is a compound formed in vivo, and this compound has antibacterial effect. So this is an observation, and after that various different classes of sulfonamides as antibacterials were developed, and for this work the Gerald Domark received Nobel Prize in 1938. So this is how antibacterial sulfonamides were developed. Now look at the chemistry of sulfonamide. This is a general structure of sulfonamide. This is aniline group, right? And look at this. This is your sulfanilamide, that is para amino benzene sulfonamide. Now this compound contains two nitrogens. This sulfonamide nitrogen is assigned as N1, while this amine nitrogen, it is N4. So there are N1 and N4 nitrogen atoms in this sulfanilamide. This sulfanilamide is a lead molecule for development of various different sulfonamide class of drugs available as antibacterials. Now this is one sulfamethazine. So look at the structure of sulfamethazine, where there is a pyrimidine ring, and the pyrimidine ring is attached to N1 at its second position, and this pyrimidine ring is substituted with two methyl groups at 4 and 6 position. So its chemical name is N1 4 6 dimethyl 2 pyrimidyl sulfanilamide. So this is basic sulfanilamide, and on this sulfanilamide 4 6 dimethyl pyrimidine is substituted. Okay, so this is what is chemistry of sulfonamides. Moving to the next, how it shows antibacterial effect. So that is mechanism of action of sulfonamides as antibacterials. Look at this. These are folate coenzymes, and these are required for humans as well as for microorganisms, including bacteria, for their different biochemical reactions which are taking place, and these are required for their multiplication. So these folate coenzymes are synthesized in humans, particularly from a folic acid. This is a folic acid, and humans receiving folic acid from their diet, and this folic acid is converted to dihydrofolic acid, then tetrahydrofolic acid and different folate coenzymes. So this is how in human folate coenzymes are generated and which are used for their cell multiplication. But the bacterial cell is not permeable for a folic acid which human receives. Bacteria are parasites but their cell wall is not permeating folic acid from the humans. So bacteria, they have to generate their folate coenzymes on their own, and they are generating their folate coenzymes by this pathway, that is by using guanosine to pyridine diphosphate, and this pyridine diphosphate and para-aminobenzoic acid. These two substrates binds to enzyme DHPS, dihydropterin synthase. This is enzyme structure of DHPS, where a PABA, that is para-amino acid, binds and a pterin moiety binds to form dihydropteroic acid. From this dihydropteroic acid, it forms dihydrofolic acid, then tetrahydrofolic acid and folate coenzymes. So this is how a bacteria generate their folate coenzymes, and sulfonamides, they are being structurally similar with PABA, para-aminobenzoic acid. They competitively inhibit binding of para-aminobenzoic acid to the enzyme DHPS. So instead of PABA, the sulfonamide binds to the DHPS and this chain terminates. So it prevents biosynthesis of folate coenzymes which are required for bacterial multiplication, and it shows bacteriostatic effect. Now, because there is competitive inhibition, you can see what is competitive inhibition. It depends upon the concentration. So you must have heard that sulfonamides are inactive as antibacterial when there is a pus formation in a wound. The reason behind is, when there is a pus formation, there is a more amount of para-aminobenzoic acid, and the dose of sulfonamide given, that is comparatively not sufficient to competitively inhibit para-aminobenzoic acid, because there is much more amount of para-aminobenzoic acid present in the pus. So the sulfonamide class of antibacterials are ineffective when there is a pus formation. So this is a kind of competitive inhibition. You can say that sulfonamide competitively inhibit PABA to show bacteriostatic effect. It prevent biosynthesis of folate coenzymes which are required for various biochemical processes in microorganisms. So the bacteriostatic action, no multiplication of the bacteria. Look at this. This is a dihydrofolic acid, a structure of dihydrofolic acid. It is further converted to tetrahydrofolic acid, and these are various folate coenzymes. This is a structure of various folate coenzymes given. See, this dihydrofolic acid is converted to tetrahydrofolic acid by enzyme folate reductase or dihydrofolate reductase. There is one more compound or one more drug that is showing antibacterial effect by acting at this site by inhibiting folate reductase enzyme, that is a trimethoprim. In subsequent slides, we may discuss about how these sulfonamides and trimethoprim in combination shows synergistic antibacterial effect. Then look at this. Major issue with sulfonamide treatment is it causes crystalluria. The crystalluria means it is not eliminated properly in the urine and it forms agglomerates, it crystallizes, and there is chances of blockage of the urinary system. So there is a relevance of this crystalluria formation and pKa value of the sulfonamides. So what is pKa? pKa is a pH at which it shows ionization. Now look at this sulfanilamide and its N4 acetylated metabolite, they have their pKa value 10.4. It means it ionizes at 10.4 pH. It gets solubilized at 10.4 pH. But look at the pH of urine. The pH of urine is around 6 or below 6. So the pH of urine is not sufficient to cause solubilization of sulfonamides whose pKa value is 10.4, and it is not easily eliminated and it gets accumulated into the urinary system, and this is what is crystalluria. Now to avoid crystalluria, either we have to increase urine flow by giving more fluids, by more intake of the water, or increase pH of urine by giving some alkalinizing agent, carbonates, bicarbonates like that, or prepare sulfonamide analogues whose pK is lower. So here are the list of different sulfonamides whose pKa is around 6.5 to 7. Here 6.5 for sulfadiazine, sulfamarazine 7.1, sulfamethazine 7.4, sulfisoxazole, its pK value is 5, whereas sulfamethoxazole, the pK value is 6.1. So these are quite comfortable and they can be eliminated easily because they are solubilized, or they are in soluble form at the urine pH, and no complication or minimum risk of crystalluria formation. So this is what is a correlation of pK values of the sulfonamides and its major side effect like crystalluria. Now this may be the reason you can see that the sulfanilamide, it is a lead molecule for the development of sulfonamide class of drugs, but sulfanilamide has not been approved as a drug. It is not being used in a clinical practice as a drug because sulfanilamide itself is toxic. So the structural modifications in the sulfanilamide have been done to generate various sulfonamide class of antibacterials which have a minimum toxic effects and more beneficial effects. Then structure activity relationship of sulfonamide class of drug. Look at this. This is a general structure of sulfonamide, where this is N1 nitrogen, this is N4 nitrogen. The basic requirement for sulfonamide class of drugs to show its antibacterial effect is that the amino group is very important and it should be directly connected to the benzene ring to show its structural similarity with para-aminobenzoic acid, because it is a competitive inhibitor of para-aminobenzoic acid. To maintain its structural similarity, this amine should be intact and it should be directly attached to the benzene ring. Then N4 amino substituted sulfonamides, they are either prodrugs or inactive. What I told is it should be unsubstituted for its antibacterial effect, but if at all it is substituted, it will act as a prodrug, means it will not show its action outside the body, but when it is administered, it breaks down. This substituted or substituent on this amine will be released, leaving free amino group in the body, and it shows antibacterial effect. Then N1 ionized salt is active. This N1 should be in an ionized form, and the maximum activity will be observed in sulfonamide class of compounds with pK between 6.6 to 7.4. So these are various structure activity relationship parameters for sulfonamide class of compounds for its antibacterial activity. Then different sulfonamide analogues were developed right from a lead molecule, that is sulfanilamide. by a substitution at N1 nitrogen. That is substitution on sulfonamide functionality. Look at this. All these analogs, they are being developed which are having substitution at amide nitrogen. Now this is sulfadiazine, sulfamethazine. Look at the structural difference between sulfadiazine and sulfamethazine. In both cases, there is pyrimidine ring common which is attached to N1, but in sulfamethazine that pyrimidine ring is 4,6-dimethyl substituted. At 4 and 6 position, 2 methyl groups are substituted, whereas there is unsubstituted pyrimidine nucleus. So this is a structural difference between sulfadiazine and sulfamethazine. Look at the chemical names. 4-amino N2 pyrimidinyl benzene sulfonamide, where it is 4-amino N 4,6-dimethyl 2-pyrimidinyl benzene sulfonamide, right? Then next one, that is sulfisoxazole and sulfamethoxazole. Again, the common features in this is substitution of isoxazole ring at this nitrogen, amide nitrogen. The isoxazole ring is connected to amide nitrogen at its 5 position in sulfisoxazole, whereas it is connected through its 3rd position in sulfamethoxazole. Then here there is disubstitution. There are 2 methyl groups substituted at 3rd and 4th position, where there is only 1 methyl group as at 5th position. So this, though they both compounds have isoxazole nucleus, there a pattern to the attachment to the sulfonamide nitrogen is different. The chemical names are here. Then sulfamethysole and sulfapyridine. In sulfapyridine, there is a pyridine moiety connected to this sulfonamide nitrogen through its 2nd position, whereas in sulfamethysole, this is thiadiazole moiety, thiadiazole heterocyclic nucleus connected to this sulfonamide nitrogen. These are different sulfonamide analogs which are generated from basic sulfanilamide. Now, if we look at the duration of action of sulfonamides, when we think of duration of action, it may be short acting, intermediate acting, or long acting. Short acting compounds, they absorb fast, at the same time they are getting eliminated fast. So there will be, or their action will be for a short period of time. The sulfisoxazole, it is absorbed fast, eliminated fast. So it has a short duration of action. If you look at sulfamethysole and sulfadiazine, they have some intermediate action, intermediate duration of action. Sulfamethoxazole, it is also intermediate acting. Its duration of action may be from 10 hours to 17 hours, whereas sulfadoxine, it is absorbed slowly, eliminated slowly, and it shows its action till 7 to 9 days. So these are the long acting sulfonamides. So the duration of action of sulfonamide will be dependent upon its rate of absorption and rate of elimination, or in other words, the duration of action will dependent upon how long the drug will remain in the body above its minimum effective concentration. So till that it shows its action. Now here, as earlier I quoted, that sulfonamides are combined normally with diaminopyrimidine class of compound like trimethoprim to show the synergistic effect. The best combination available is trimethoprene and sulfamethoxazole. The brand is Septran or Bactrim or cotrimoxazole. So this shows synergistic effect because both these drugs act on same pathway at different stages. Now, which pathway they act on? That is biosynthesis of folate coenzymes. And this sulfonamides act at the dihydropteroid synthase enzyme by competitively inhibit para-aminobenzoic acid, whereas a trimethoprene act in the next step by inhibiting enzyme dihydrofolate reductase, which is required for conversion of dihydrofolic acid to the tetrahydrofolic acid. So because of this combination, the same pathway will be blocked at two different stages, and it shows synergistic effect. Synergistic effect means 1 plus 1 is equal to 3, more than the addition. So this is how this Bactrim or Septran or cotrimoxazole is used in combination to show the better improved antibacterial activity. The sulfonamides are available in the form of its prodrug. The prodrug I already quoted that these are inactive outside the body, but when they are introduced into the body, they release its active form of drug and shows the desired effect. This is a sulfasalazine. If you look at the sulfasalazine, then this fourth nitrogen is substituted, forming a azolinkage. When this sulfasalazine is introduced into the body, it breaks down its azolinkage, releases this free amino group which is required for its antibacterial effect. So this is how the sulfasalazine act as a prodrug for sulfonamide class of drugs. The another class of sulfonamide, you can say it's a dapsone, that is 4,4-sulfonyl bisbenzene amide. So these two benzenes are bridged by SO2 group, and there are two amines substituted on the benzene. Now these dapsones shows its antibacterial effect even with some structural variations like substitution on both 4 and 4' amino functions. Even though these two amines, if they are substituted, still it shows antibacterial action. If the one amine is substituted, that is mono substitution, it also shows antibacterial effect. Even this benzoid portion, if it is substituted with some groups, it shows the effect. And even if one ring is replaced with some heterocyclic ring, still it is active as an antibacterial. So this is how the dapsone shows antibacterial effect with a similar kind of mechanism as that of sulfonamides. Thank you. We'll stop here.